Assalamu alaikum. This is lecture number 2 of control systems, and this will also comprise of the topics of Laplace inverse and Laplace transforms. Previously we have studied that in order to take Laplace transform, the function is going to multiply with e to the power minus s of t. We take out integration from 0 to infinity dt, and time will be eliminated. The rest of thing will become function of s. So f of s will be a frequency domain function or Laplace function, where s is sigma plus j omega. I already told you that sigma is equivalent to 0 while j omega is varied from 0 to infinity. Few other examples will be present in the next slide. Okay, similarly in this equation f of t is equal to a e raised to the power minus alpha t ut, we have introduced a scaling coefficient a and e raised to the power minus alpha t, where alpha is constant of decay. So if the values of alpha are more, e raised to the power minus alpha t will decay down at smaller values of t. In this equation, if we apply the same formula of Laplace transform, that will multiply this with f of t with e raised to the power minus st and integrate it over time from 0 to infinity. This 0 to infinity will change, will include the limit of u of t. U of t just tells about that it starts from 0 and it exists till time t is equal to infinity. So this is absolutely summable function, and we know that e raised to the power minus alpha t is a convergent function. It is not going to expand, it is going to decay. So when it is multiplied by e raised to the power minus st, which is also a convergent function, the product of these two convergent functions will make a convergent function, convergent solution at the end, and it will be absolutely summable. That's why we can find out Laplace transform. So the other functions having more growth rate, more than exponential, will not be absolutely summable, and hence it will not be integrable, and hence Laplace transforms will not exist. But we'll not talk about those functions whose growth rate is more than exponential. So let's talk about this function. So f of t is e raised to the power minus alpha t. Let's plug in this equation f of t e raised to the power minus s of t. So we'll have the cumulative product form is something like integration from 0 to infinity. A comes out of the integration because it's just a constant, e raised to the power minus s plus a times t. Now this is integrable function, and the answer is e raised to the power minus s a, e raised to the power minus s plus a t, and divided by s plus a, and limit goes from time t is equivalent to 0 to infinity. So similarly, likewise, previously we did substitution of higher limit first and minus lower limit. So we'll have a divided by s plus a times e raised to the power minus infinity, which is 0, minus e raised to the power 0, which is 1. So minus will come out, and that will cancel with the previous minus sign. So we'll have the total Laplace transform function as a divided by s plus a. This can also be verified. Now this function, which is a e raised to the power minus alpha t u of t. Now we know that e raised to the power minus alpha t is rotation in time domain that will change into translation in s domain, and from the tables we can we can figure out without having any integration that its Laplace transform is a divided by s plus a. Likewise, we can apply other functions with the integrations, and we can also apply the tables to confirm that whether we have done right or wrong. In short form, there is no need of applying integration unless it is told, and you can find out Laplace transforms by using tables as well. So here we have another example of sinusoidal, and f of t is cos omega t. We want to find out the Laplace transform of cos omega t. Finding out integration, multiplying it f of t with e raised to power minus t will generate a productive form of two functions, and we can apply integration by parts, and that will be a lengthy process. So why not to convert the cos omega t into its Euler's identity? Through Euler's identity, we know that f of t is equivalent to 1 by 2 e raised to power j omega t plus 1 by 2 e raised to power minus j omega t. Now this function is easy to integrate because the exponentials will get add up when f of t is going to be multiplied with e raised to power minus st. So this e raised to power minus st will be combined with e raised to power j omega t, and will have easier solution as compared to the integration by parts. So let's apply Euler's identity to decompose cos omega t into constituent product exponential functions. That's why I've told you earlier in the previous lecture, in the first lecture, that any function can be generated with the help of cos omega t or sin omega t or exponential functions. We can generate any type of functions. Fourier said it in 17th century that we can decompose any type of signal into its constituent sinusoidal functions, and using that statement, we can do a reverse order by adding few exponentials or adding few sinusoidals to make any type of function. So let's come back to the Fourier transforms, to Laplace transforms. F of s is equivalent to integration from 0 to infinity e raised to power minus st times f of t. Now f of t will be decomposed into half e raised to power minus j omega t and e raised to power minus j omega t separately. As integration is has commutative property, it has associative property, it has distributed property, so it can be equally distributed on both functions. So we have first function as half of integration starting from 0 to infinity. Exponentials will get add up, and it will be e raised to the power minus s plus j omega t dt, and the other half portion is 1 plus 1 by 2 integration from 0 to infinity e raised to power minus s of t minus j omega t dt. And if we apply this integration, we'll have half 1 divided by s plus j omega t and half s minus j omega t, and we can take LCM of s minus j omega and s plus j omega. That will become s square plus j omega square, and on the numerator side we'll have s. Similarly, we have to define the constants of the region of convergence, and the region of convergence is for s is greater than 0. But we don't have to talk about region of convergence right now, because that will be studied more in details in Z transforms or digital signal processing. Another common function is t raised to the power n, or t square, t cube, t raised to the power 4, or t raised to the power n. Any type of function can be entertained with the help of this type of function f of t is equivalent to t raised to power n, where n is greater than 1. Means t is expanding with time. So if we have let's say n is equivalent to 2, it will be t square curve, which is exponentially, which is growing. And similarly, t raised to power q will grow faster than t raised to power 2. Similarly, t raised to power 4 will be faster than t raised to power 3. But everything, when it is got multiplied by exponentials, it will exponential is going down, like e raised to power minus st is decaying function, and it is controlling the exponent, it's controlling the expansion, while t raised to the power 1, 2, 3, 4, 5, it is going to expand. So what will be the ultimate solution when highest polynomial of t raised to power n is got multiplied by e raised to power minus s of t? The total solution is convergent. Now my wording is important, as we can simulate it with the help of MATLAB, we can simulate it with the help of Excel, or we can show that any highest power of t can be made convergent with the help of e raised to power minus s of t. So if we have t raised to the power n, it will be multiplied with e raised to power minus s of t, and limit will go from 0 to infinity. This is what we want to find out, f of s. So if t raised to power n is a first function and e raised to power minus s of t is another function, then we have to apply it. We have to find out solution with the help of integration by parts, and there is no other solution possible. So we have to apply the integration by parts, and the total solution that we got at the end is f of s is equivalent to n factorial divided by s raised to the power n plus 1. So if we have, let's say, if we have a function of t square where n is equivalent to 2, so f of s will be 2 factorial divided by s raised to the power 2 plus 1, which is 3. So the f of s will be 2 divided by s raised to power 3. Similarly, for t cube, the answer is 6 divided by s raised to the power 4. Similarly, for t raised to power 4 and t raised to power 5, we can find out any type of we can find out any power of t that will be having f converted into f of s with this formula. So so far we have done delta t, we have done u of t, we have done e raised to the power minus alpha t, we have done constant, let's say a times e raised to power alpha t, we have done sinusoidals, and we have done multiple powers of t. So multiple powers of t means any type of polynomial. When it is going to be converted into its Laplace transform, we can use these integration processes, or we can do the tabular form process. Similarly, we have, let's say, impulse which exists at t is equivalent to 0. Then f of t will be delta t, and impulse is something like this function, that it has got existence only at t is equivalent to 0, and when it is got integrated over time, it will give 1. So when f of t is going to be integrated out with multiplication of e raised to power minus s of t starting from 0 to infinity, it will give me its Laplace transform. So let's apply Laplace transform. Delta t e raised to power minus s of t, and as delta t only exists at t is equivalent to 0, so the e raised to power minus s of t is only existing at t is equivalent to 0. So let's find out whatever is in the argument and substitute it in place of e raised to power minus s of t, and that is e raised to power 0, which is 1. So when this has got 1, the integration comes out to be 1, and we have got solution of impulse. Similarly, for f function e delta t raised to the power k, which is kth derivative, so that can be translated also in terms of s raised to the power k, where k is the kth derivative of delta function. In the previous lectures, that integration process was discussed in detail, and we know that integration process is a linear function, and linear function has properties of distributive and commutative, even associative properties also present in this function. So it's a linear process. As integration is a linear process, eventually linearity is true for Laplace transforms, because Laplace transforms are based on integration. So the Laplace transform is linear if f and g are any signals and a is any scalar. We have Laplace transform of a times f, that is a times capital F. Similarly, Laplace transform of two functions f plus g, that will be capital F plus capital G. So this Laplace will be equally applied on f separately and then g separately. Later they will be added on, and that's the definition of linearity. You must remember that when two functions are linear, any function applied on those linear functions will be separately applying a linear function on each function, and then later on adding will get a similar result. Similarly, homogeneous process and superposition process, if that processes holds, then the system will be linear. Another definition of linearity that we have discussed in electronics was that if the set of frequencies present at the input is equivalent to the set of frequencies present at the output of the system will be linear. This definition is much simpler, but has more depth in understanding. Normally people only use this definition of linearity, that those processes which holds homogeneity and superposition are linear. But the other definition that we have discussed in electronics 2 is also true, that if we have set of frequencies at the input and set of frequencies at the output of the system, they are equivalent, then the system will be linear. Let's take the example of linearity and Laplace transform here. Let's say the function is 3 plus delta minus 2 e raised power t. Then the Laplace transform will be applied separately on 3 times delta t and separately on 2 e raised power t. So if we apply Laplace transform on the first function, that is 3 plus delta t, 3 comes out of the function, and Laplace transform will only be applied on delta function, and we know that Laplace transform of a delta function is 1 constant. So we have, for first function we have just 3, and for second function it is a rotation that will change into translation in S domain, and e raised to power t will be converting into 1 over s minus 2, where 2 is a constant, so we can keep the total function as 2 divided by s minus 1. So if we take LCM of 3 minus 2 divided by s plus 2, we'll have s minus 1 at the denominator and 3s minus 5 at the numerator. We can prove it by taking LCM. So the cumulative transfer function of 3 delta t minus 2 e raised power t is 3s minus 5 divided by s minus 1. Let's talk about time scaling. When the system is something like g of t, let's take g of t as a signal, and then that's equivalent to f of a plus t, where a is a constant and that is multiplied with t, and if a is greater than 0, then time will be changing fastly in g as compared to in a. Then g of s is equivalent to 1 over a times f of s divided by a. That makes sense. The time are scaled by alpha. Frequencies will be scaled by 1 over alpha. Let's check it. Let's say g of s is equivalent to 1, its integration of f of at e raised to power minus st, where integration goes from 0 to infinity. Then it is we can set another variable tau in placement of t, and we change the limits of integration. So if tau is equivalent to a times t, then everything is changed. Now the 1 over a comes out of the integration constant, and it is integration from 0 to infinity, the same, and f of tau e raised to power minus s divided by a times tau and d tau, and the answer is 1 over a times f of s over a, where tau is a times t. So without doing any type of integration, we may reach to the result that if, let's say, if we have a function as an example, we have e raised to power t as 1 over s minus a. So function in time domain is going to change into Laplace domain by 1 over s minus a. Let's say if we have e raised to power alpha t in place of e raised to power t, then we can use this property, time scaling property, to get the answer of Laplace transform, and it is 1 over a times, so we'll replace everywhere, instead of s we'll place s over a, and 1 over a will be coming out of integration. So 1 over a multiplied by 1 divided by s divided by a minus 1, and the answer is 1 over s minus a. We know that e raised to power alpha t, we have confirmed it through process of integration, that it is 1 over s minus a. Similarly, we can also prove it with some other type of with another type of method. That method is tabular form method, and we know that translation rotation in time domain will change into translation in s domain. So we can apply any of these processes in order to find out e raised to power alpha t Laplace transform of this function. In previous lecture, we have seen the time scaling property. Now this time it is time delay property, and that the function is delayed by a few amount. Let's say if let f be a signal and t is greater than capital T is greater than 0, defined as signal g as g of t is equivalent to 0 for t between 0 to capital T, and f of it has value of f of t minus tau for values greater than capital T. So if in simple words, f of t and g of t both are mentioned in the figure below, where g of t is a delayed signal. You may see that g of t is starting out later in time domain. So let's say if the corner is if the starting point of g of t is equivalent to 0, then g of t, actually the function starts after some amount which is capital T, and that becomes the delay. So if the function is delayed, whether it's Laplace transform will be found out through integration process, or there is anything other process which is possible that we want to find out in this example. So in the next page, or in the next slide, we'll try to represent time delayed signal, and without having any integration we can find out the Laplace transform. Obviously, logic says that, or duality principle says that, if rotation is going to change into translation in S domain, this is translation in time domain, that must be changed to exponential or rotation in S domain. So I must be expecting something like e raised to the power S in the Laplace domain, because now it is time which is delayed. There is a translation in time domain that will ultimately be changing into rotation in S domain. So let's see the next slide to confirm the statement. Okay, let's see uh, if g of s is a function, then it will be equivalent to e raised power minus st capital T, where T capital is the time delay in the time scale times f of s. So g of s is equal to e0 from 0 to integration from 0 to infinity e raised power minus st times g of t dt. That will be translated into integration from capital T to infinity e raised power minus st f of t minus capital T, where f of t minus capital T will be equivalent to g of t. Similarly, we can do the conversion in the scale, time scale, and let's put t minus capital T is equivalent to tau, and if we substitute it, e raised power minus st will become e raised power minus s tau plus capital T times f of tau d tau starting from 0 to infinity, and that will be e raised power minus st times f of s. Now, as I said in previous slide that the translation in time domain will going to be changed into rotation in S domain, and this slide confirms that it is rotation in S domain, where rotation is e raised power minus s capital T, and translation in time domain is like f of t minus capital tau. So duality principle says that time domain translation will change into rotation and frequency domain, and rotation in time domain will change into translation in frequency domain. So both are equivalent. Now this can be used to find out any type of Laplace transform having translation in time domain. Okay, in this slide we'll talk about derivatives of the function in time domain. So let's say if f is a signal, continuous signal, and it exists at time t is equivalent to 0, then if the derivative of f is represented as f bar, and we want to find out Laplace transform of derivative of the function, then it will be translated as Laplace of f bar, where f bar is derivative of f, is equivalent to s times f of s minus f of 0, where f of 0 is initial condition of time domain signal. So first derivative will change into first multiplication of s. The two double derivative will change into s square f of s. Similarly, third order will change into s cube f of s, and so on and so forth. So the point is that time domain differentiation become multiplication by frequency variable s, as with phasor, plus a term that includes initial condition, that is minus f at 0, where f is the signal in time domain and 0 is its initial condition when function is equivalent to, when time is equivalent to 0, what is the value of f. That will be substituted here. So applying higher order derivatives, applying derivative formula twice yields, let's say Laplace transform of f double bar is Laplace transform of f bar minus f bar at 0. So let's apply another time Laplace transform. It is s times f of s minus f of 0 minus f bar 0, and that will become finally the last equation, which is s square f of s minus s times f of 0 minus f bar 0. Similarly, in the same manner, we can find out if we have third derivative, what will be its Laplace transform. Similarly, generally, we can state a formula for having any kth derivative. So let's say Laplace transform of f of k is to be measured or to be explored, then we can apply the formula given in the next slide. But you can always generalize from the first equation that what will be the f of k. So there is no need to remember all these formulas. They will be either provided or they can be extracted with the help of integration or some other process. So let's take f of t is equivalent to e raised to power t, and its derivative is f bar t is equivalent to e raised to power t, because the derivative of e raised to power t is the same, and we want to find out the Laplace transform of a derivative of the function. Then the derivative of the function f bar is equivalent to 1 over s minus a, using the formula let's say of f bar. And what is the formula of s bar? It is s times f of s minus f of 0, small f of 0, mean time domain signal f of 0, and the time domain signal f of 0 is 1, because e raised to power 0 is 1. So let's apply this formula here. So it is s, so this first s is coming from the formula, and f of s, we know that f of s is 1 over s minus a, minus 1 is coming out of the formula, that it is the value of initial condition of time domain signal at time t is equivalent to 0. So this one is minus 1 is from there. So if we have this formula, then we can take the LCM. It is 1 over s minus a in total, which is the same as the derivative of, which is the same as the function provided in f of t. Similarly, if sine of omega t is equivalent to 1 over omega derivative of cos omega t with a negative sign, then Laplace transform of s of omega t will be equivalent to 1 minus 1 over omega, and this s, the first s that's coming out, that first s is from the formula where f of s is, for the cos omega t it is s over s square plus omega square, and minus 1 is from the time derivative values, the function values in time domain, and that is 1. So it is, the total function comes out to be, it is omega divided by s square plus omega square. So there is no need, if we know the formula of if we know the Laplace transform of cos omega t, we can extract the Laplace transform of sin omega t with property from a property, and that property is mentioned here. So in general, another one is f minus unit ramp. F is a unit ramp, so f bar is a unit step function. Then f bar, Laplace transform of f bar is s times 1 over s square minus 0. So this first s comes out from the formula. 1 over s is the Laplace transform of unit step and unit ramp, and minus 0 is the value coming out of f of 0, which is 0. So it is 1 over s. So in this slide, we can find out derivation of derivative formula starting from definition of integral. So if it is f bar t, it is got multiplied by e raised to power minus s of t, and the limit starts from 0 to infinity. Integration by parts yields first function is, let's say, e raised to power minus s of t, and the second function is f of t. So the definition of integration by parts is that first function comes out as it is, and the second function is integrated out minus integration of second function times derivative of first function. So this is the general definition of integration by parts. Now we can apply this definition in order to get the definition of g of s, and the g of s is stated as s times f of s minus f bar 0, which is presented in this slide. Few more examples about application of derivative. Let's say f of t is equivalent to e raised to power minus t, and g of t is equivalent to t e raised to power minus t, and we want to find out Laplace transform of t e raised to power minus t. Then we know that it is it is multiplication in time domain that will change into derivative in s domain. As derivative in time domain changed into multiplication of s in s domain, so now this time it is multiplication of time within time domain that will change into derivative in the s domain. So let's apply the derivative in s domain of e raised to power minus t. The Laplace transform of e raised to power minus t is 1 over s plus a. So we'll take first derivative with a negative sign, and that will give us the Laplace transform of t times e raised to power minus t, which is 1 over s plus 1 whole square. Similarly, let's say if f of t is known, that is t e raised to power minus t, and g of t is t square e raised to power minus t, then we want to find out the derivative, the Laplace transforms of t square e raised to power minus t. As we know that the Laplace transform of t times e raised to power minus t is 1 over s plus 1 whole square. So let's say that it is got multiplied by another t, which means that it will be integrated out, it will be derivative out one more time with a negative sign. So 1 over s plus 1 whole square will get derivative with a negative sign with respect to s. So d by ds with a negative sign times 1 over s plus 1 whole square, and that will be going to have 2 divided by s plus 1 whole cube. Similarly, in general, if we want to have a Laplace transform of t raised to the power k e raised to power minus t, then it will be k minus 1 factorial divided by s plus 1 times k plus 1, where k is the power of highest power of t. In general, we can say that each time when t is multiplied with the function, then each time the function on the s domain will get derivative with a negative sign with respect to s. Similarly, convolution in time domain will change into multiplication in frequency domain, and multiplication in time domain will change into convolution in frequency domain. Vice versa is also true. The convolution of a signal f and g is denoted by limit integration starting from 0 to t f of tau g of t minus tau d tau, and that will become the convolution of f of t multiplied by f of t and g of t. So this process is complicated process. That's why we want to change this complicated process into simple process of multiplication by taking these functions f of t and g of t both in the frequency domain, and then they will get multiplied. So let's say f of t has Laplace transform as f of s, while g of t has a Laplace transform of g of s. They will get multiplied in the frequency domain or Laplace domain. Vice versa is also true. So finally we have this table, and this table simplifies all the previous things that we have studied so far. It has got time scaling property, it has got linearity property, it has got multiplication with a constant, it has got rotation, translation, scaling. So every property is present, and we need to apply this table rather than finding out any type of function by integration process. Yet integration process can also be applied, but the answer that we'll be getting out of the integration will takes lot amount of time. Rather than taking lot amount of time, we can find out immediately using these tables. Similarly, this is another part of the table. And this table states that if the derivative exists in the function f and the double derivative and the higher derivatives, then how can we find out solutions in frequency domain? So that's all for the process of taking Laplace transform from time domain to frequency domain. So we'll use these formulas rather than finding out Laplace transform through integration process, and hence concludes the lecture number 2 of this